الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. Is it recording?
Yes.
Yes.
Yes, it is.
Last thing I talked about was actually Bohr equation. Very important. You have to know the name. Bohr, great scientist, and he made this relation, which is the relation that you're seeing here. What did he discover, or what did he propose? What's this constant, by the way? We took it last time. What was it? Rydberg constant. And what does Bohr says? That this is the nucleus, and what's around it?
Electrons.
Which atom we're talking about?
Hydrogen.
Only hydrogen, H, not H2 gas, H atom. H atom, that's what we're talking about. What did he propose? That we have the nucleus, which has how many protons? Hello?
One.
One proton.
One. Good. And then what's around it?
Electrons.
Circles. Okay. Each circle has energy. What's the energy of each circle? It's this energy. Okay. And he called the first one n equal to what?
Integer number.
And where is the electron? Where is the electron?
On one.
It's in, when it's in what? If it's in one, what will happen? It is in which state?
Ground state.
Ground state.
Unexcited.
Ground state. How about if it goes to 2 or 3 or 4 or 5 or 10?
Excited states.
Excited states. Excited states. Okay, when it goes from 1 to 2. Okay, so first, can you calculate what's the energy of N1?
We put N2 minus N1. 1 over N2.
What's the energy of N equal to 1?
Minus 2.18 multiplied by 10 to the power minus 18.
Okay, Joule times what?
1 over 1.
Yes.
1 over 1.
Okay, what's the energy of N equal to 2?
It is the same multiplied by 1 over 4.
Exactly, so minus 2.18 times 10 to the power minus 18 times 1 over 4. And if I want N equal to 3?
Multiply 1 over 9.
Multiply by 1 over 9.
Very good. Now, can we have the difference delta E of 2 to 1? If I go from 2 to 1.
Would there be a negative charge?
It will equal E2 minus E1.
Which is E2 minus E1. Clear? And you can calculate it this way. Now, if I'm going from n equal to 1 to n equal to 2, like this way, is this going to be exothermic or endothermic?
Exothermic.
No, endothermic. Going from 1 to 2 is endothermic. Why? You want to take something from lower energy to higher energy. Clear?
It will absorb.
It will absorb energy. Exactly. From 1 to 2. How about we go from 2 to 1?
Exothermic.
Exothermic.
So this process from 1 to 2 is exothermic. This process is this is exo, and this one is endo.
Endo.
Good. Okay. Now instead of these circles, we're going to make it lines. So we'll put the nucleus here, and instead of the circle, I'll put it lines of energy. All right. These lines are exactly the lines that we saw here. These are the lines. So this one is n equal to what? 1 n equal to, oh sorry, this is n equal to 1. So n equal to 1, n equal to 2, n equal to 3, n equal to 4. Can you see them? These are the circles, but instead of the circle, I'll put them like energy. Clear? So this one is equal to n equal to 1, n equal to 2, n equal to 3, n equal to 4. Clear? And we can, where is the electron? It could be here. If it's here, what do we call this state?
Ground state.
If it's here,
Excited.
first excited state. This one, second, third, and so on and so forth.
Third.
Okay. Now, let me let's stop here. Okay. Good. All right. Good. Okay. We talked about this already, and then other people calculated all the energy from every energy. See, these are the lines that we talked about. These are the n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, n equal to 7. Can you see them? Again, did you see this picture before from here to here? Did you see it before? Did you see it here? Do you see it here?
Yes.
It's exactly n equal to 1. Look here, the distance between 1 and 2 is big, and then it gets smaller and smaller and smaller and smaller, and that's exactly, they made all the calculation and they came up with all these relations. And these scientists calculated how much energy, by the way, when we draw the arrows like this, is the energy going to be exothermic or endothermic? Exo, all of it is exo. Okay, Layman calculated the energy to go to the n equal to 1. From 2 to 1, from 3 to 1, from 4 to 1, from 5 to 1, 6 to 1, 7 to 1. He calculated the amount of energy exactly for all these transitions. And then Palmer, what did he do? The transition from where?
From any number to 2.
From any number to 2. Okay, how about passion?
From any number to 3.
To 3. And then bracket?
To 4.
To 4. Here, that's all what they did. They just sit down and calculated the exact amount of energy. Is this easy or difficult?
Is it the same for all elements?
No, this is just for hydrogen atom. We're talking only about hydrogen atom. Only.
Doctor,
Yes.
can you repeat it?
As I said, we're talking about hydrogen atom. We came up with these lines, which are exactly the same like these lines that we saw in the picture. And this is n equal to 1, n equal to 2, n equal to 3, n equal to 4. Now we have them this way. And this is n equal to 1, n equal to 2, n equal to 3, n equal to 4, 5, 6, 7. And then these scientists, Lehman, Palmer, Paschen, Brackett, calculated this amount of energy going from n equal to 2 to n equal to 1, n equal to 3 to n equal to 1, n equal to 4 to n equal to 1. And they came up with all these lines. They calculated the exact amount of energy for all transitions. Do you notice anything about this, the shape in this picture? What do you see here different for all the transitions other than the other transitions?
Balmer series.
Balmer.
Well,
Color.
you see it. Colored, while the rest you don't see them. They put them as black. Okay, what does that mean? Palmer series happen in what?
In the light we can see, or color we can see.
In what? What do you call it?
Visible light.
Visible light.
Visible light.
Take place in visible light. Exactly. Clear?
Yes.
Okay. Now use Bohr. What's Bohr energy? What's calculate the wavelength for emitted when an electron transition from n equal to 4 to n equal to 2 state in hydrogen atom. Can we do that? What's delta E? Equal to what?
Minus 2.18.
Minus 2.1. You don't have to memorize this. It's available in your periodic table. Take it from the periodic table. 2.18 times what?
10 to the power minus 18.
What? Joule. Times what?
1 over 4 square
Square.
minus 1 over 2 square.
No. From n equal to 4 to n equal to 2. How should you write it?
The opposite.
The opposite.
The opposite, yes.
You have to write
1 over 4 minus 1
1
over
2
6.
square minus 1 over 4 square. Give me an answer quickly.
Minus 4.08 multiplied by 10 to the power of minus 19.
Minus 4.08. Yes?
Multiplied by 10 to the power of minus 19.
What's the unit?
Joule.
Joule.
Joule, of course. It's the only unit here. These are unitless. Everything is unitless except this joule. Good. Is this clear? Is this easy or difficult? How can you find lambda?
Lambda equal
Or
1 over lambda equal
what? HC over lambda. We took this already. So what's lambda equal to?
delta E over HC.
No, reverse.
HC over E.
E. Exactly. What's H?
Planck constant.
Planck constant. You have to use the name. What's the speed?
Speed of light.
Sorry, speed of light, of course. What's C? I mean, it's the speed of light. Yes. And what's delta E? We already calculated. Give me lambda quickly.
Minus 4.87 multiplied by 10 to the power of minus 7.
Lambda cannot be, lambda is a measurement, so don't use the minus or the plus because it's for, we use plus or minus for energy. For wavelength, don't just give me number.
4.87 multiplied by 10 to the power of minus 7. 4.87 multiplied by 10 to the power of minus 7.
Who got the same answer?
Yes, doctor.
I got
I
it.
got it.
Yes,
What's
doctor.
it?
Doctor?
What's the unit?
Meter. And you need nanometer.
Because it's
Meter.
joule, everything is here, and the speed is meter per second, and this is joule, so it's meter, exactly. That's the answer. Okay, clear?
But one step still.
Well,
We have one step. 2 nanometer, he said.
okay, very good, very good. Make it in nanometer, excellent.
Doctor? 10 minus 2.
10 to the power what? Plus 2 nanometer. 4.87 times 10 to the power plus 2 nanometer. And let's see, is it correct? Oh, it's not written here. Let's see. And there's this number. This is 1 over lambda.
A.
Okay, next. Very good. I hope you got this. Next. The other thing that we're going, another scientist that we're going to talk.
Doctor, we can't hear you or see your screen.
اتوقع طلع دكتور.
فصل عليه أعتقد.
تو يدخل الدكتور.
السلام عليكم.
عليكم السلام.
وعليكم
وعليكم
السلام.
السلام ورحمة الله.
Anyway, let's continue. Okay.
We can see your screen.
What? Oh, you cannot see it on screen, of
Your
course,
screen.
because I've been. Yes. All right. Yes. The second person that I want you to memorize the name very well is de Broglie. De Broglie. De Broglie hypothesis, very important hypothesis. What's the de Broglie hypothesis? He said that things or the waves can have nodes. The waves, of course, when you have a wave like this and another wave or like this, if we have waves between lines, these points are called nodes. So how many nodes do we have here in the first one? How many nodes?
2.
2.
No, 0. Oh, the sides, don't do it. Don't talk about the side. We'll talk about the middle. How many nodes do we have in the first one? 0. How about
0.
how many nodes we have here?
1.
1.
And
One.
here?
2.
2.
Okay, and he said that the electron must be having perfect nodes. Why? Because the electron, the shape will be like this. So see here, 1, 2. I mean, this is three waves, and these must have exactly the right nodes. Okay, but this one will not work. Why? Because the circle is not complete and the waves will cancel each other. Not important. What I want you to know, the proposal of de Broglie, if we have a circle This must be 2 by r. 2 by r. Well, what's 2 by r?
The circumstance.
What? Circumference. Exactly. Circumference of the circle. The circumference of the circle must equal to lambda. What's lambda?
Wavelength.
Wavelength.
Length. Okay. Times n. What's n? The one that Bohr talk about, which is equal to 1, and equal to 2, and equal to 3, which are what's called? What are these called?
Power level.
Integer.
Not power.
Integer.
Energy level.
Energy level, exactly. All right, so this is the first equation you must memorize very well for de Broglie. 2 by r equal to n lambda. Don't forget it. 2 by r, which is the circumference, equal to what? N lambda. What's n?
Energy level.
Energy level. What's lambda?
Wavelength.
Wavelength. And what's 2 by r?
Circle circumference.
The circle.
What's r in particular?
Radius.
The radius.
Radius of the
What's
circle.
by?
3.14.
14, yes, 3.14, exactly. Good. And then there is another theory he came up with, very important, you must memorize and memorize very well, that lambda equal to h over mu. I will write it here so that we will write everything about mu. What's lambda?
Wavelength.
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 Very important. What is h?
Planck
Constant.
constant.
Planck constant. Very good. What is m?
Mass.
Mass
Mass.
of electron or anything. It could be for an electron or anything. Okay. What is u?
Velocity.
Velocity.
Velocity. Okay. What does this equation tell us? That you can change mass to light or change light to mass. Is this clear? Is this
Yeah.
clear?
Yes,
Okay.
sir.
Now we will do it right away. Memorize this equation. We'll solve a problem just right now. Lambda equal to h over mu. Let's solve this problem. Calculate the de Broglie wavelength of a particle in two cases. First, if we have a bullet, which is 25 grams, traveling at speed of 612 meter per second, what's lambda? Don't forget, h equal to 6.63 times 10 to the power minus 34 J or joule. All right, tell me what's lambda. I need an answer right away.
Doctor. Doctor.
Yes.
Mass should
Oh.
be in gram or what?
Oh,
It is
good.
4.17.
Just a second. The mass should be in gram or what?
Kilogram.
Yes,
Kilo.
you have to change it to kilogram because joule, because when you change joule, it must be kilogram meter square per second square. Okay, so what's lambda? Change this to kilogram first.
4.3 times 10 to the power minus
4.
35.
And 10 to the power minus 35 meter. Okay, so we calculated the wavelength of a bullet. Of course, everybody knows bullet is what? Particle. But when we talk about wavelength, what do you mean? Light. So we change the bullet to light. Okay, tell me, but see at the number here. Is this possible? 4.3 times 10 to the power minus 35. This means you have a 0 and then 34 zeros before you reach 4. 34 zeros, which is For us, it's 100% nothing at all. It's impossible almost. Okay, good. How about if we have electron? This is the mass of electron moving at speed of 63 meters per second. What is lambda? Go ahead, calculate it quickly.
(1.15 multiplied by 10 to the power minus 5.
1.15 what? 1.15 what?
Multiplied by 10
No.
to the power
No, not.
154.
Huh?
meter.
154.
154 only?
622.
1.54.
Times 10 to power minus 5.
I have it in this slide as 1.16. That's okay.
I got 1.155.
Yeah, that's what I expect. 1.155, which is 1.16 times 10 to the power minus, what?
Minus 5.
Minus 5.
Minus 5.
Meter, which is reasonable. Now we have lambda with 5 zeros only, and after 5 zeros we'll have the wavelength. Is this clear? I hope so. Good. Then another scientist, it's not very famous name, but Thomson, he noticed that if he diffracted the electron, he will see waves like this. And so he said the electron could be what? Mass, could be particle, or what?
Wave.
Wave. The electron could be particle or wave, and this is called dual. Dual means two. Dual means two. Dual function of electron. What's the dual function of the electron?
It could be particle or wave.
Or wave. This is already done by de Broglie also. Answer, yeah, de Broglie. Okay, how about light? Light also will have double function. What? It could be what? Waves
Particle. Wave.
or particle. What's the name of the particle?
Photon.
Photon.
So the light is called what? What function does it have?
Dual.
Dual.
Function.
What's the meaning of dual function?
Have two states.
Two states. Fantastic. Okay, next, the uncertainty principle. You must memorize the name. Uncertainty principle. Memorize the name and memorize it very, very well. All right? And the uncertainty principle, it's a difficult principle. I'm not going to explain it much for you. I want you just to know the name. What's the name?
Uncertainty principle.
Uncertainty.
Memorize the name. What's the name of the person who made it?
Heisenberg.
Heisenberg.
Heisenberg uncertainty. Heisenberg uncertainty principle. All what you need to know about this is delta X times delta P is greater than or equal to H over 4 lambda. What's delta X?
A change in the displacement.
Error in what?
Position.
Position or place. Oh, I like position much more. I want to say place, but I will erase it and I will write position. Error in position times what's delta P?
Momentum.
Error in momentum. What's momentum?
M times U.
M times U. Exactly. So this will be error in delta MU. And what's H?
Blank.
Echelon constant.
And what's 4 by? Of course, 4 times what?
3.14.
3.4.
Exactly. Okay, so this is the uncertainty principle when we change momentum into m delta v. Okay, all what I want you to know, write this equation. We will solve a problem right away now using this equation. And that's all what I want you to know about uncertainty principle. Okay, done? Let's go and solve this problem.
Doctor,
Yes.
it will not be in the final or the mid?
Of course, it is the final. What do you mean? Very important equation. I'm almost 100% sure you'll see it in the final.
Okay.
I wanted to memorize this equation, and I can tell you there will be a question in the final about it. Okay, what does this equation say? The error in position times mass times the error in speed is greater than or equal to h over 4 pi. Good. Okay, an electron in hydrogen atom known to have velocity of 5 times 10 to the power plus 6 plus or minus 1%. So what's delta V? Or delta U, we call it U as well. What's delta U? What? Come on. 5 times 10 to the power
10 to the power
6 times 1 over 100. Plus or minus 1%. That's the error. Clear?
We don't need to write the signs.
The plus or minus, this is the error. Yes, it is plus or minus. You can say it's a plus or minus this number. But this is the error, right?
Yes.
Okay, what's the answer?
5 times 10 to the power
4.
4. Okay, that's the error in the speed velocity, u. Okay, using the uncertainty principle, calculate the minimum uncertainty in position. So what's delta x? Give me an answer. H over 4.
We can't know.
Divide by what?
times 10 to the power 4.
Mass times delta U. Because this is the momentum. Okay. The question is asking, calculate the uncertainty in position. That's the uncertainty in position. And we're using this equation. This is delta x equal to what? H over 4 lambda divided by m delta u. Okay, so it's divided by m delta u. So give me an answer. The mass is given to you here. It must be in kilogram. Don't forget. And this is the error.
1.06 multiplied by 10 to the power minus 39.
Cannot be.
0.
I guess 1.16 times 10 to the power minus 9.
Yes, I like that.
Doctor, will put it equal or greater than or equal?
Oh, you don't have to, but yes, it's greater than or equal, but we're going to use equal, of course. So the error is 1.16 times 10 to the power minus 9. Minus 9. Okay, what does that mean? If we know the length of the radius in calculation, the radius of hydrogen atom is calculated now. If this is a hydrogen atom, the radius when n equal to 1, the distance for hydrogen atom from the nucleus to the electron is equal to 1 times 10 to the power minus 10. Is this clear? This is the distance. This is calculated by other people. This is called 1 times 10 to the power minus 10 is called 1 angstrom. So what's the radius of hydrogen atom? Radius
1A.
Radius of H atom is equal to 1 angstrom. Don't memorize the name, angstrom. What's angstrom?
10 to the power minus 10.
10 to the power minus 10 meters. But look at the error, 1.16 times 10 to the power minus 9, 10 times as big as, so if you know the radius, the error in here is 1000% more. The error is plus or minus 1000.
Can you repeat the last point, doctor?
Okay, the radius here is 1, this is the radius, delta x, which is the radius, is equal to 1 times 10 to the power minus 10 meter, plus or minus 1000%.
How did we know?
Okay, calculate 1 times 10 to the power minus 10 times 1000 divided by 100.
Mr. Isn't it the half of 1 angstrom because it's the diameter? So we need to divide by 2.
No, this is the, given that the diameter, yes. Yes, this, okay. Maybe he's talking about the whole diameter then. The whole diameter, so yes, very good point. I did not notice it myself. But the 1 angstrom is for diameter. It says already. And the position we're talking about the whole diameter. So yes, the position here is diameter. So the diameter is 1 times 10 to the power minus 10. The error is 1000%. Why? Multiply 1 times 10 to the power minus 10 times 1000 divided by 100. What's the answer? 1 times 10 to the power
minus 9.
Minus 9, which we calculated here. So you can see the error is huge. And that's why the uncertainty principle of Heisenberg is important. Is this clear? Very good.
Doctor.
Okay, good. Then another extremely important name I want you to memorize very well. It's called Schrödinger. Schrödinger equation. All right? Schrödinger equation. Memorize it and memorize it very well. All what I want you to know about Schrödinger equation, he developed what's called the wave function. Memorize the words. What's the name of the scientist? Schrödinger. What's the name of the equation that he developed? What is it called?
Wave function.
Wave function. Wave function. What's the wave function? It's psi. And that's all what I want you to know about this equation, because it's a complicated equation that you don't have to think about. This is, so what's psi?
The wave function.
For what? For which element?
Electron. For hydrogen.
Atom. For electron, but it's for, we're starting with hydrogen atom. We're starting with hydrogen atom at the beginning. Okay, how do you pronounce this letter?
Psi.
Psi, you don't pronounce the P. Okay, so you say psi is the Schrödinger equation. That's all that I want you to know. It's wave function and it's called psi. Is this clear? Okay, now another important thing about Schrödinger equation, we have what's this?
Psi.
Psi
square.
Psi square will be finding the probability of finding the electron. What is it for?
Probability.
Probability to find the electron, probability to find the electron, and this is psi squared here, very important name. So what is this? What's this letter?
Psi.
Psi.
Psi. What's psi?
The wave
Wave
function.
function.
Wave function. Okay, and what's this?
Psi squared.
Psi squared. What is it? What does it calculate?
The probability of finding electron.
Very important two terms you must memorize. Who developed these two?
Schrodinger.
Now, there's something beside. What do you mean by psi? You can think about it this way. Psi is equation only. So if I have a wave like this is not, of course, the electron wave. It's one of the waves. Can you represent this wave by a wave function? If this is y and this is x, can you make a wave function to represent this wave?
Yes.
Yes.
Sine.
What?
Sine.
Sin x.
Sine x. See, you developed the wave function for this wave. That's the wave function. Okay, and what's sine? It's equation to represent what? The wave function of
Electron.
Electron wave. The electron is wave, and this one is to represent wave. It's a wave function. Electron wave. Or electron wave. So the electron now we treat it with as wave. Now they start solving this equation and they came up with what's called electron density. Psi squared tell you electron density. Now the electron is not a particle. If I ask you in your room now, where is the room? Where is the light in your room? Where is the light in your room?
Everywhere.
Everywhere. How many lights you have there? You cannot tell how many lights. It's just a light there, right? Exactly. Now, if you think about the electron as a particle, where is the electron in this shape? Where is the electron?
Everywhere.
Everywhere.
How many electrons are there?
We can't do.
We cannot tell, but it could be one or two. If we have one or two, let me ask you another question now. In your room, there is maybe one light or two lights. If we have only one light in your room, hello. If you have one in your room, where is the light going to be?
We can't hear you.
Doctor, there's a problem with your mic.
Okay, can you hear me now?
Yes.
Okay, one more time. If you have in your room, if you have one light only, where is the light going to be? One bulb, you know, bulb of light. Where is the light going to be?
Everywhere.
Everywhere in the room, right? All around the room, right? How about if we have two lights, not one, two bulbs? Where is the light going to be? In the room, right? What's the difference between the one light or the two lights?
The amount of light.
Exactly. So how many electrons do we have here? It could be one or two. What will be the difference if we have one electron or two electrons in this shape? What's the difference between 1 electron or 2 electrons?
The two will have more density.
Exactly. So this will be electron density will be higher. Is this clear? Hello. After solving the Schrodinger equation, they start having what's called the 4 quantum numbers. I will stop here, but before I stop, I want you to memorize this slide extremely well. You have to know the name, principal quantum number, which we did before by Bohr. Okay, and then angular momentum quantum number, L, magnetic quantum number, ML, and electron spin quantum number, MS. I want you to sit down today, and tomorrow we'll continue the lecture. Today, memorize just these 4 names extremely well, and tomorrow I will explain to you what's the relation between them, and we will finish the whole chapter 6 based on these 4 lines only. And I will stop here. It's time to stop. All right, and let's go to attendance, please, as usual. And let's open the attendance, and it's open for 3 minutes. And I'm not going to reopen it. Go ahead, take attendance. If you are not around, or if you go to bathroom, or you just left, sorry, I'm not going to reopen it.
Okay, just can you give us 2 minutes?
نعم.
بس تعطيني دقيقتين بس عندي معلش شوي بس الوقت.
Doctor.
Yes.
How can we see our